Hi there. My name is Peng. I am a software engineer on the data platform team at Nextdoor. I've been here for about a year and a half, and today I am here to talk about why Nextdoor ditched a data warehouse for a centralized data lake. So just to give a little context about the data infrastructure at Nextdoor, Nextdoor's data infrastructure is a hybrid data lake to data warehouse model. It's sort of pretty industry standard. There is, there's a data lake that we house that's mostly S3 data, and then that is then piped up to a traditional data warehouse. We use Redshift, but any sort of data warehouse works. In terms of data volume, we do process about 55,000 jobs per day on Spark, Presto, and Hive. We kick those jobs off via Qubole. In terms of data volume, that's about 10 terabytes of data per day, 8 billion rows. Nothing, by industry standards, this is big data, but not super big data. This usually equates to about 200 nodes running on average at any given point in time. So, the need for distributed data is there. And one of the main things that we also do are super into on our philosophy is this concept of pipeline as configuration. We want to emphasize, anyone any employee of Nextdoor can write ETL pipelines to build on this sort of democratized data lake. So that's sort of the state of the Nextdoor world for data. I'll go a little bit more onto the data architecture side. We have our data stores that we sort of ingest the majority of the data from. And a lot of this, these data stores are, traditional RDBMS. These are not multi-region data stores. These are independent databases in each region, AWS region specifically. And what we do is, we have a sidecar container that listens into the transaction logs of this database, and then writes that to Kinesis, which then writes it to Firehose, and writes it to an S3 bucket in our raw data lake here. These infrastructure groups are replicated for every single region. So, in US West 2, in Oregon, we'll have this for the Nextdoor and Atlas table, which serves US. And then conversely, in EU West 1 in Ireland, we also have the exact replicated infrastructure that serves all the countries that we're active in Europe. This is all piped down to the S3 buckets in Northern Virginia. And then on top of that, we have some third-party API data that comes in, whether through Salesforce data, Google Ads data that any sort of REST API data that can come into this S3 buckets, we sort of pull them in here. And then that's sort of where our data processing pipeline takes over. We house an Airflow cluster, and that schedules a series of tasks, the overwhelming majority being in Qubole, to schematize, process, clean, scrub the data, and do some light pre-aggregation to write to this, a process data lake. And I kind of want to talk about this little red box here up at the top. This is where Redshift, the data here is piped up to Redshift for visualization for Tableau, or, at various use cases all across the company. We've historically used it for ad reporting, so revenue reporting, ad inventory forecasting, reports, dashboards, basically sort of a one-stop shop for the data visualization at Nextdoor. So that little red box right up there, it became very clear very fast that this is going to be the bottleneck of our entire data pipeline. The analytics query and data volume, quickly outgrew the Redshift cluster. We were running on a pretty beefy cluster that 6 nodes. I think it was 200 cores, 10 terabytes of memory, 100 terabytes of storage, but it still just kept growing at an aggressive pace. We've had to scale it up a couple times, but it got to a point where scaling up just wasn't financially economically feasible anymore. So these cost concerns meant we had to start selectively funneling data sets to Redshift from the data lake. So you could only choose a subset of the data sets that in S3 to upload to Redshift, and then on top of that you had to have relatively aggressive deletion policies. And so these data sets could only stay for 14 days or 30 days, and you can kind of imagine why that would be a big issue for a lot of forecasting, a lot of historical backfills or back testing. So that became a pretty big constraint for a lot of that family of jobs. There was also the operational overhead. I'll talk briefly about my team. We, as a data platform team, we're actually a very small team of only started off as only 3 to 4 people, and a lot of the work that we had to do to maintain Redshift, managing the monitors, a lot of help debugging, why is my query not working, trying to build tooling around making Redshift performant, all of that operational overhead, on the join keys, the commit queues, the paging of certain cluster usages and storage limits, that all that maintenance and overhead led to a huge time sink on the team that we just wanted to get out of. I'll speak about the data pipeline also a little bit more. I think each data set had now has 2 table representations. We have a Hive external metastore, that's sort of a pretty industry standard of Hive external tables describing what the data is in S3, and then we also have it replicated in Redshift. And so while that was not the hardest to maintain, it was only 2 sources of truth. Schema evolution, became a huge issue for us. So if we wanted to update, add a column to our biggest, some of our biggest tables, altering a table in Hive would be very, very easy, but in Redshift it would lock the table up for hours, and so then we had to plan that downtime, and then there was also schema inconsistencies, so it led to a lot of headaches when trying to do schema evolution, especially on an automated basis. And then there's this problem of a single commit queue for Redshift. This becomes a huge bottleneck for writes, because our data was changing very fast every hour. We were uploading new versions of the data every hour, and so this commit queue was always full. And so if some users just got unlucky and ended up waiting almost hour for just a simple select query. And so this sort of bottleneck became very constraining for us. And so around in late 2018, we started thinking about a solution to get around this. And like any good planning for a solution, you think about what your solution what goals it's trying to solve. And so here were basically our objectives that we kind of stated out. We wanted to reduce the engineering time enabling data analytics and BI. A lot of the time, many of us would get pinged over the course of the day, say, "Hey, why is my SQL query not running in Redshift?" And that's 90% of the time, it turned out that it was because Redshift was slow. And then the other 5% of the 5 to 10% of the time, it would turn out that there were type differences between Redshift or whatever other problems that were specific to that did require our involvement. And those were the problems that we wanted to spend time thinking about, not debugging why is my Redshift query slow. So that was a big thing. We wanted to also lower the barrier to entry to query the data. So a little bit of a backstory here. I think Redshift is an AWS product. It is, to sign on to get access to query Redshift, you need AWS access. While this is good for, perfectly fine for engineers like myself. There were people on marketing teams that needed access to Redshift to do investigative queries, and that was simply not possible without sort of a workaround. They had to get an engineer to work on, or needed temporary access. So that sort of behavior and usage pattern didn't exactly mesh well with how we wanted to query the data. We also wanted to empower more users to have a deeper understanding of the data. And so, I think, given the fact that we selectively funnel data sets up, a big issue is that the owners of the data sets, the dashboards which do this funneling, they have the model data model built up in their head. And if you want to add a feature to a dashboard, add a new graph, add a new column, you basically have to go through them to be able to get that feature added. And because that's a bottleneck on people, that just simply doesn't scale as the company grows. And so we wanted other users to be able to explore, poke around with a much lower barrier to entry. We also wanted to ensure, data processing costs are within reason. I think the cost of our Redshift cluster was 20% of our budget, and it did processing on significantly less than 20% of the data that we had. And so, if we're okay with having a higher cost for data processing given the data volumes, but we do want to make sure that the data costs provide at least equal amounts of value to it, however that is measured. And then, just as a baseline, you want to provide reasonable data SLAs. You don't want to, we weren't in a streaming mindset at this point in time. So, but we don't need immediate, sub-second or sub-minute SLAs, but we do want, sub-2-hour SLAs, which is sort of what we had before. So, looking at possible solutions now, what could we do? One thing, the most obvious one is, triple the size of Redshift, right? This is the classic throw more money at the problem kind of solution. This would, solve, the MySQL query is no longer slow, but still has the pain of the schema migration the schema inconsistencies and the operational overhead. This doesn't exactly solve our problem. And on top of that, as the size of Redshift gets larger, the cost of it becomes significantly the cost efficiency of it becomes significantly lower. We're a North American based company, or at least the majority, and so the majority of our queries are coming in, North American business hours, and so overnight, as the cluster's sitting idle, because Redshift couples storage and compute, the cluster sitting idle there is just an extremely expensive S3. In fact, I think at the cluster size that we were at, it was 5,000 times more expensive than S3. And so, sitting like that for half the day is just not worth it. And as you increase the number of nodes, it just gets continually more expensive. So, you could look into other options like a serverless data warehouse. Google BigQuery is the biggest, the most obvious example. They're on the more extreme side of managed data warehouse. They've solved the problem of storage. There's a storage cost and then there's a compute cost, but they still are able to provide a very, very fast query time. That while that sounds nice, the Nextdoor is an AWS shop almost exclusively, and a migration into a completely different cloud provider with completely different practices was a large undertaking that wasn't outside the scope of this project, and so that didn't exactly work either. And so I think the third solution, you can see the spoiler alert coming here. Basically, the idea was, why don't we just dump Redshift, use the common metastore that we have already, and then use Presto as the warehouse engine, right? Presto has been, since version 193 has been incredibly fast. It's shown to have hold everything in memory and be quite performant, especially in a VPC. I'm just gonna here's the architecture diagram of what we had before. Redshift is up there in the corner, but here's what we ended up doing. And I don't want to go too much into the conversation about Looker versus Tableau, the visualization platforms there. We did have a sort of a secondary migration on that, but the idea is that you could do this the same as in Tableau as you would right now in Looker. But the idea is that Looker now is connected to Qubole, and it leverages Qubole to process the S3 data and then run aggregations and then return that data to Looker for visualizations and reporting. So the data architecture is significantly more simplified now. You don't have this clunky data warehouse that's there. But there were a few things before we had migrated. There were a few things in Redshift that it did provide out of the box for us, and that we needed to replicate in a S3 file system manner before we could fully migrate. And so the two main things are read isolation and security and permission. And so I'll talk about read isolation first. And so what read isolation is that if you have a current view of a table, we'll take user profile is one of our biggest tables. In Redshift, as a write transaction is occurring, if there's a select transaction on that table, you'll see the current view of the table until that transaction is complete, right? And then you'll see the new changes. You'll never see partial data, or you'll never see duplicate data, right? So that's sort of the concept in transactions that Redshift provided out of the box for us. Obviously, if you can't really do that in S3 file systems, because as you're writing to a particular folder file system, and you have an external table backing that, if you happen to get unlucky as the table is writing or rewriting, deleted all the data, you could run into a partial data set, or you could run into duplicate rows or something like that. As we go towards read isolation needs to be replicated in a file system manner. And how we did that was we essentially create, for every single table that we managed, we constructed two tables. This concept of a snapshot table and this concept of a view table. And so the snapshot table is partitioned by a DS or timestamp or whatever time series, and it in that particular partition that describes this is the view of the table at that particular moment in time. And we would just continue, once a new partition came in, we would write to it, once a new ran occurred, we would write to that table, and so on and so forth. And then we have this view table that would point to that particular partition. And so, as you see that the table has a newer table has completed writing, it would modify the pointer, and only on completion of that. So essentially mimicking a transaction, and basically continuing onwards like this. We would, after the September 3rd has been written, we would now point to that new partition. Cool. So talking briefly about securities and permissions in Qubole, I think Qubole has authentication. That's great. I think the authentication level is a little different than permissions are a little different than AWS, and so that works well. But I want to go a little bit more in depth about how we manage permissions and roles and whatnot. And so we decided to go even deeper on this, and what we decided to do is we split have multiple Qubole accounts by usage profile. And so in traditional data warehouses, the the queries are always read heavy, and so what we did was we split up between this what we call an ad hoc account. This is the data warehouse usage profile. It's going to be incredibly read heavy, and then there's going to be like a production account which does a lot of the writing into the file system. Conversely, the ad hoc database account does not have read permissions into these data warehouses. You can also have different profiles on these the clusters themselves that do this do the writing to it. In the ad hoc account, we know that because it's super read heavy, and the usage is going to be very spiky. We can afford errors, and we can afford we're optimizing essentially for cost more than stability, and so we have aggressive auto scaling policies. We heavily leverage spot nodes both in upscale, and then we want to aggressively downscale as well. In terms of the production account, whereas we want a significantly more stable environment to conduct these writes. We leverage a higher percentage of on-demand nodes, and don't our hedge on stability more than performance. So the state of the data in 2020 now. I think given from what we've seen, I think the one thing to emphasize, I think, from this presentation is that we committed fully to a storage only data lake with Qubole as the compute engine. More specifically, the Presto on Qubole as the data warehouse engine, and this has worked wonders for us. Historically, if Tyler in marketing ran a huge query in Redshift that was running for 3 hours, it would bork the entire cluster, bung up the entire cluster, and everyone would start complaining about why Redshift is so slow. Now, if Tyler ran said huge query, we would be able to spin up a cluster, a new Presto cluster for other people to run their queries on, or just increase the max node cluster size on Presto, and that would that flexibility of the decoupling storage compute. I think that can't go understated, because the flexibility to scale up on resources on that is incredibly powerful. It comes down to an API click as opposed to management and debugging, and just a bigger time sink into investigation. We also have one source of truth now, right? So there's the Hive metastore. That's pretty standard. Very, very easy to manage from our perspective. We love to continue using it, and we are. There's nothing much to be said about that. And then one thing, the accessibility to data is basically democratized across the entire platform. I think this is, data discoverability can't be understated, because a lot of the, now in this new world, it isn't just the data scientist going in. Anyone can build a dashboard, anyone can go in and look at all the hundreds of tables that we have that across the platform, and they have the ability to query and explore on visualizations, and that is a huge power to us across the platform. I guess I can't go without speaking about the concession of performance. I think the reason Redshift can be incredibly performant is that it couples storage and compute together. So large scale aggregations on billions and billions of rows can happen incredibly fast, because they know where the data lies in terms of on storage, and you're decoupling that here. However, it's not as bad as you expect. The Presto cluster that we spin up resides in our AWS VPC. The buckets, the raw data, the S3 buckets that we use for our process data lake and raw data lake are all living on a NAT gateway that peer into this VPC. So the network transfer bandwidth, is incredibly fast. It gets up to 150 megabytes per second. If you include compression on that, that's about 300 megabytes to up to 500 megabytes per second on network transfer and data transfer. So you'd be hard pressed to find you'd be hard pressed to find performance, cluster performance, go at the rate of 500 megabytes per second. So there are use cases in which there are heavy joins that do suffer performance hits, but overall, a lot of aggregations and counts do perform adequately within 20 seconds on large tables of greater than 20, 30 gigabytes of data. So it's the concession of network bandwidth is still the limiting factor, but it's not. It gets pretty close to the compute cap that you have in a given Presto cluster. So I kind of want to just end on talking a little bit about the future work that we have now available, that we've sort of pushed out this new data infrastructure. One of the biggest things is that I'm particularly excited about is the richer feature sets that are enabled. ML, you can run a join on 30 to 40 tables, have a table of anywhere to 100 to 300 columns and of certain features describing a particular user, and now you can run a lot of ML training or inference or scoring regression on these features, these large tables, and this is all because we can discover all the tables that we have in our centralized data lake. There's also performance implications. We want to improve some of our biggest fact tables are running into scalability concerns, but we're excited to sort of figure out performance benefits from that. Bloom filters are one thing that we're looking into. HBase on top of S3 as a data store, as a data processing unit to speed up certain joins and certain queries. And Hive on Acid, these are all sort of potential performance gains that we're all looking into, and basically all unlocked by the fact that we have a simple S3 file storage and it's backed on Qubole. So yeah, that's my presentation. Thank you for listening to this my talk. Yeah, I'm Ivan Peng. I am a software engineer at Nextdoor. If you found this presentation interesting, or if you found what we're doing at Nextdoor interesting, please feel free to reach out to me or take a look at the Nextdoor careers page if you find anything interesting. Cool. Have a good day.